Imagine standing on solid ground, feeling the earth beneath your feet, when suddenly it begins to shake. That jolt of uncertainty, that moment of fear, is something we all hope to avoid. Earthquakes are nature's most unpredictable challenges, and when they strike, they don't care about our plans or our infrastructure. This is where the responsibility of engineers comes into play, especially when it comes to critical structures like dams and hydraulic systems. Today, we're diving into the U.S. Army Corps of Engineers guidelines for designing earthquake-resistant concrete hydraulic structures. And trust me, it's more fascinating than it sounds. Let's start with the Engineering Manual EM 1110-2-6053. This isn't just a dusty old book sitting on a shelf. It's a comprehensive guide that lays out the seismic design and evaluation process for these vital structures. The purpose is straightforward. We want to ensure that these structures can endure the seismic hazards they might face, maintain functionality, and most importantly, prevent catastrophic failures that could endanger lives and communities. Now, when we talk about seismic events, there are two key players that guide our design approach. First up is the operating basis earthquake, or OBE. Think of this as the kind of shaking you might experience every few years, frequent but moderate. Our structures need to be able to withstand this without suffering significant damage. They should be operational, ready to serve their purpose, and not look like they've just been through a blender. Then we have the maximum design earthquake, or MDE. This is the big one, the rare, severe event that could potentially cause immense destruction. Our goal here is clear. Structures should avoid collapse, even if some repairs are needed afterward. We want them to stand strong, no matter how fierce the shaking gets. To make this happen, we define performance levels that describe how these structures should respond. First, there's serviceability performance, which ensures that after an OBE, everything remains functional. Imagine a dam that can still operate its floodgates just fine after a moderate quake. That's what we're aiming for. Next is damage control performance, which limits the damage during those rare MDEs to what can be repaired. Finally, we have collapse prevention performance, which is all about avoiding catastrophic failure under extreme conditions. It's about safeguarding lives and infrastructure, and it's a responsibility engineers take seriously. The manual also highlights 3 structural behaviors that we need to consider. Ductile behavior is our best friend here. It allows structures to deform significantly before they fail, effectively dissipating the energy from an earthquake. Then there's limited ductile behavior, where deformation is a bit more constrained but still provides some resilience. On the flip side, we have brittle behavior, which is something we strive to avoid. When a structure fails abruptly, it's not just a design flaw, it's a potential disaster waiting to happen. So, how do we actually design these structures? It all starts with load combinations. For strength design, like OE, we combine MDE loads with dead and live loads to ensure that we're preventing collapse. For serviceability design, we combine OBE loads to make sure everything remains functional. It's like building a bridge between the expected and the unexpected. To ensure our designs meet these ambitious goals, we rely on evaluation methods. For instance, we need to keep tensile stresses in concrete within elastic limits during an OBE. When it comes to an MDE, we analyze controlled cracking and sliding to ensure stability and repairability. It's a meticulous process, and every detail matters. Let's take a real-world example to illustrate this. Picture a gravity dam. Under OBE conditions, we want to ensure that there's no tensile cracking, keeping the dam operational. In the event of an MDE, we allow for some controlled cracking, but we ensure that the dam won't collapse. It's about preserving integrity while acknowledging the forces at play. The same principles apply to other structures like spillways, locks, and intake towers. Now, local seismic hazards are crucial in determining the ground motion demands. Engineers use response spectra and time histories to model how structures will respond. Site-specific spectra take into account local geology, ensuring that the designs match real conditions. It's like customizing a suit to fit perfectly. No two locations are the same. Material properties also play a critical role. Reinforced concrete must have sufficient tensile and shear capacities to handle those seismic forces. Designs need to avoid brittle failures by ensuring proper reinforcement ratios and details. It's a delicate balance, but when executed correctly, it leads to robust structures. Stability is essential too. Engineers evaluate sliding and overturning tendencies at foundations or interfaces. Nonlinear methods help predict how structures behave after cracking, ensuring that the damage is repairable rather than catastrophic. It's all about creating a safety net, a cushion that absorbs the shock and keeps everything intact. By following the design criteria outlined in EM 1110-26053, engineers craft hydraulic structures that balance safety, functionality, and resilience. These guidelines aren't just technical jargon. They represent a commitment to protecting communities and critical infrastructure. Seismic design is both a science and an art. With thoughtful application of these principles, we're not just building for today, we're building for generations to come. So, the next time you cross a bridge, look at a dam, or even just walk on solid ground, remember the incredible work that goes into ensuring that these structures can withstand the unpredictable forces of nature. It's not just engineering, it's a promise to keep us safe. And that's something worth celebrating.